Metals, nonmetals, and metalloids are all components of the periodic table. The diagram seen here shows a nice layout of each of the types of elements. So metals comprise the vast majority of the periodic table, and they're represented here in yellow. Your nonmetals are represented over here in the green, and your metalloids are found along the stair step here. Being comfortable with the layout and the identification of each of these types of elements without the specific diagram is obviously going to be necessary. However, that's a skill set that I assume most of you already have. So metals. Metals are basically any elements that exhibit the chemical and physical properties that are associated with metals. So good conductors of heat and electricity, being malleable and ductile. So malleable is basically able to be shaped and molded. Ductile means that it can be drawn into wires. Metal oxides are ionic solids and basic. They have a shiny luster and can be various colors, but most are a silvery type of hue. They tend to form cations during reactions, meaning that they are oxidized in reactions, and they are characterized by having low first ionization energies. If we look at the chart that we were viewing in the previous slide, you notice that metallic character increases to the left. Obviously, that's not going to be including the hydrogen atom here because it's a nonmetal. And going top to bottom, the metallic character also increases. So these are just the basic features of metallic elements. And make sure that you're familiar with each of them, and we'll talk about some of the details here in a moment. So as I said earlier, basically metals are typically going to be found in ionic compounds. Basically the combination of a metal and a nonmetal is going to produce that ionic compound, such as we see here. So if we take sodium solid and chlorine gas, if they react, you get sodium chloride, which is a salt, or an ionic compound. You have two ions that are bound together. As I said earlier as well, most metal oxides are basic. And more specifically, if we look at a few reactions, soluble metal oxides give you hydroxides when they're placed in water. So if you take sodium oxide or calcium oxide and you add them to water, they will give you sodium hydroxide and calcium hydroxide respectively. And the basicity is due to the reactivity of the oxide ion in solution. So the oxide ion interacts with the water to give you hydroxide ions. Now that we've discussed soluble metal oxides, insoluble metal oxides will react with acids to basically produce a neutralization setup. So nickel oxide is an example. If we mix that with nitric acid, we will end up with nickel nitrate and water. So basically we neutralize this strong acid that we have here with the basic nickel oxide that we have present. Furthermore, the insoluble nickel oxide will not dissolve in water, as you can see down here. It's insoluble. However, when you place it into the nitric acid, this neutralization process occurs, and it ends up dissolving the nickel ions as well as the nitrate ions into the solution. This is why you see this greenish hue here due to the ions present in the solution. So nonmetals are typically found on the right-hand side of that periodic table. Those green elements on the previous chart that we were looking at correspond to these types of elements. They do not have a shininess or a luster, and they're typically different colors. As you can see over here, the sulfur is kind of a yellowish color. Nonmetals are poor conductors of electricity and heat. They're very brittle. As you can see here, this sulfur breaks apart into kind of a crumbly mess. They tend to form anions in reactions, so the reduction process is what happens to them. So nonmetals typically pick up electrons. So we can see this here. Basically, we have the noble gas electron configuration of bromine, the neutral bromine element. We add an electron to it, and that gives us a bromide ion. So notice I go from having 5 electrons in my 4p orbital to having 6. So that's the normal process that most of them want to undergo. Some do it with more than 1 electron. as you guys are familiar with. Compounds containing only metals tend to be covalent substances. And most of the nonmetals are gases, liquids, or very low melting solids. If we look at the nonmetal oxides, they're going to behave quite differently than the metal oxides that we discussed previously. When we put nonmetal oxides, in this case carbon dioxide, into water, they're going to give us a corresponding acid in solution. So our carbonic acid will be produced when these two are combined. Similar truth is real for this compound. This should be an oxygen. This should be P4O10. I apologize. When you mix that nonmetal compound containing compound with water, you end up with phosphoric acid, as you see here. Because of the acidic properties that are the acidic compounds that are produced when we put these nonmetal oxides into water, nonmetal oxides are of course going to react with bases to give you the neutralization process, much in the same way we saw the reverse process happening with the metal oxide in acids. So if we take a nonmetal oxide and mix it with a base, we're going to end up with a salt and H2O, so a neutralization process. So these are the basics of your nonmetals. Metalloids are kind of how they sound. Basically, they're in between in terms of the characteristics of the metal and nonmetal elements. And also, as we saw on the chart that we originally looked like, they actually physically occur on the periodic table in between both of the metal and nonmetal groups. So we can look at something like silicone. Silicone is a metalloid, and it looks a lot like a metal, as you can see here. It looks shiny and kind of lustrous like the other metals. However, it is brittle, and it doesn't conduct heat or electricity. So it might look the part, but it doesn't necessarily have all of the chemical or physical characteristics. And we will discuss metalloids in more detail when we discuss semiconductors and dopants and things of that sort, but that will be in a little bit later chapter. For now, I just want you guys to be able to differentiate between metals, nonmetals, and metalloids, be able to share some of the details about their metal oxides or about metal oxides, nonmetal oxides, how they behave in solution. Do they give you a base? Do they give you an acid? Those types of things are the things I want you guys to be able to share. So let's go ahead and let's look at the trends from Group 1A. So the alkali metals is what Group 1A is known as. The alkali metals, or the word alkali, is from an Arabic word meaning ashes, and ashes is where some of the early alkali metals were obtained by researchers. All the alkali metals in that group have characteristic metal qualities, so they conduct electricity, they are shiny, things of that sort. And they also share in common that each of them has the lowest first ionization energy value in their period. So what does that mean? That means that they're all going to give up that first electron very easily. And this is one of the reasons why they all have the +1 charge when they form ions. Now, they do exist in nature as compounds. They are very reactive. So usually, you can take a Group 1 alkali metal, you can mix it with hydrogen, you can get a metal hydride, which we'll talk about hydrides a little bit later in this lecture. They also react with sulfur to give you metal sulfides. So the alkali metals are pretty reactive. They're also very reactive with water. As you can see here, the first three, lithium, sodium, and potassium, they all react very vigorously. They interact to give hydrogen gas, which is why we see a lot of the bubbling. They also have a tendency to be exothermic, so sometimes the hydrogen gas that's being evolved gets ignited, and that's why we see this nice little flame here. Now, alkali metals, when they interact with oxygen, have the ability to form oxides, peroxides, and superoxides. So if I take lithium, it's going to react with oxygen and just form a simple lithium oxide. Sodium and potassium, on the other hand, they are going to form sodium peroxide and potassium peroxide. And rubidium, they form superoxides. So this has a lot to do with the reactivity that we see down the period. The removal of that electron from the sodium, potassium, lithium, rubidium gets easier and easier as you go down the periodic table, which should make sense because the electron that's being removed is farther away from the nucleus. So basically they're able to be removed very easily, so the reactivity down that table is going to increase. So as you go down the table, the reactivity of the alkali metal is going to become more substantial, and you're subsequently going to go from just getting simple oxide products to superoxides. So the nearest neighbor to group 1A is group 2A, known as the alkaline earth metals. Even though they share a somewhat similar name, the alkaline earth metals are harder and more dense and typically melt at higher temperatures than the group 1A. All of the alkaline earth metals have characteristic metallic qualities, so the conductivity, luster, all that good stuff. Now, alkaline earth metals have low first ionization energy values, but they're not as low as group 1A. So subsequently, they're also less reactive than group 1A. We can see that the comparative reactivity with water is drastically different than what we saw with the alkali metals. So basically, beryllium, it doesn't even react with water. It doesn't matter if you heat it. It doesn't want to do anything. Magnesium, on the other hand, it will react somewhat with room temperature water, but it will increase its reactivity, or will react more steadily if you basically add heat and expose the magnesium to steam, so really hot water. Calcium and the elements that are below it, they do react with water at room temperature. When they react with water, you end up with a metal oxide or metal hydroxide and hydrogen gas. So depending on the type of element that you have, i.e. one that is less or more reactive, will dictate the product that you're going to get. So when the reactions occur with alkaline earth metals, they typically want to lose their 2 electrons so that they can be like their nearest noble gas. So they all like to form these +2 cations. So trends for the group 6A elements, otherwise known as the oxygen group, start with basically you have elements with non-metal characteristics up at the top, and as you approach the bottom, the characteristics become more metallic. All of the elements except oxygen are solids in their elemental state, so everything except obviously your oxygen, as I said. Oxygen is typically found in 2 molecular forms, O2 and O3. O2 represents what we typically call oxygen. O3 is ozone. And these 2 molecular forms of oxygen are known as allotropes. And allotropes are basically different forms of the same element in the same state. So basically these 2 are both in the gaseous state. They consist of the same element, but obviously they're in different forms. Ozone, as you guys may have heard, the ozone layer. Ozone absorbs specific harmful wavelengths of light and basically protects us on Earth's surface from the harmful rays that are being exhibited by the sun. Oxygen gas, we obviously breathe it. It's used in combustion. There's lots of interaction with oxygen gas that we have. Sulfur is another element that's in this group 6A, and it exists in several allotropic forms, but the most common is this S8. Sometimes people will just write S and assume that the S8 is what's being represented. Some text does that, or some texts do that, excuse me. So you want to be mindful of that. Sorry, this should be SO2. Sulfur is gonna react with oxygen in order to form, excuse me, I'm sorry about that, SO2. So when sulfur is in the air, we usually get that in the air when people burn coal or charcoal, things of that sort. Sulfur is present in these items. Basically, we put sulfur in the air, oxygen reacts with the sulfur, and that produces SO2. SO2 is a major air pollutant, and something obviously we want to try to avoid. So that's one of the reasons why we scrub our combustion byproducts and things like that with catalytic converters and those types of things in our vehicles and in production plants. All of the oxygen group elements prefer a -2 oxidation state, so they prefer to pick up the electrons. And these are the characteristics of the oxygen group. Group 7A consists of a group of elements known as the halogens. Down the group, all of them are nonmetals. As the atomic mass increases down the table, so do the melting and boiling points. So at room temperature, fluorine and chlorine are both gases. Bromine is typically a liquid, and iodine is a solid. Each one of them occurs as a diatomic molecule in nature, right? So meaning that they occur as F2, Cl2, Br2, and I2. They have very high electron affinities, meaning they desperately want to pick up that electron so that they can be like their nearest noble gas. So they're generally fairly reactive. Fluorine is the most reactive of the bunch. In fact, it's so reactive that special equipment has to be used, special containers have to be used to store the gas. Chlorine is the most useful of the halogens. It's used to purify, or I shouldn't say purify, it's used to stop the growth of bacteria and things like that, and life in drinking water and pools. And so we use it as an additive to keep our waterways safe. Bromine and iodine are commonly used in chemistry. We use them as reagents or visualization aids. So they show up in different types of chemistry. Now, I want you guys to all pay attention to the difference between the elements, such as, let's see, fluorine, okay, in its elemental form, versus fluoride. Okay, so fluorine in its elemental form, it hasn't picked up its extra electron yet. So the electron configuration for fluorine is going to be 1s2, 2s2, 2p5, while the electron configuration for fluoride is going to be 1s2, 2s2, 2p6. Okay, and this is going to be charged. Okay, there is a big difference between the behavior of these two species, right? Fluorine, the gas, is extremely reactive. As I said, it basically will react with almost anything it's exposed to. So special equipment, special handling, special containment, all have to be accounted for. Fluoride, as you've heard, we have this in our waterways, our drinking water, we have our toothpaste. Okay, obviously they are drastically different. And the reasoning behind that is basically the elemental form does not have the electron that it needs in order to be content. The anion, on the other hand, has picked up that electron. It has a full octet, and it subsequently is content. So group 8A consists of our noble gases. Noble gases, we should be thinking of them with respect to the nobility of old. Kings and queens didn't react or interact with commoners, and most noble gases do not do those types of reactions either. So all of the noble gases are nonmetals. They are monoatomic, meaning that they don't form diatomics like we saw with fluorine and chlorine and bromine. And the reason why they don't do that is because they have completely filled p and s shells. So they have an octet. They also have very large first ionization energies. The reason why they have large first ionization energies is because they have completely filled shells, their stability that's afforded that, and so moving away from that causes a disruption in the energetics of the atoms. So with that in mind, they're relatively unreactive. As I said, they don't interact with commoners, just like nobility, kings and queens don't react with commoners in daily life. There are a few of the noble gases, a few that are farther down the periodic table. They actually will form some compounds. However, if you notice the compounds that are formed with the noble gases, the other element that's being used is one of the most reactive on the periodic table. So fluorine is involved in those reactions, and being one of the most reactive elements on the table, it would make sense that that would be the one way that we would be able to get the least reactive elements on the table, the noble gases, to actually interact. So it would make sense that xenon and krypton would be the two to react, because xenon's the one farthest to the bottom, and krypton is right above it. So basically, the ones that have the lowest, the elements or the noble gases in the group that have the lowest first ionization energies are going to react with the fluorine and subsequently give you compounds. The krypton difluoride is actually the only molecular compound that is known for krypton. So these are unlikely to occur, but they do. However, most of the time, noble gases are looked at as unreactive. And this is actually very helpful in things like light bulbs. We're able to preserve filaments by adding noble gases into the light bulb, and instead of the filament in the light bulb being oxidized and ruined, you get a lot longer lifespan for that process. Oxygen-sensitive chemistry, we use usually nitrogen gas is pumped into boxes, and we have our chemicals that are oxygen-sensitive inside something called a glove box, which is what this is. And you can do your chemistry in an oxygen-free environment or relatively low oxygen content environment, and you can carry out chemistry that's extremely sensitive. Neon signs, obviously running electrical currents through gases can excite them, and you can subsequently get the de-excitation process and see this nice, beautiful glow. So the noble gases, they're relatively unreactive. I think of them as being, the haughty, stuck-up, kings and queens who don't want to interact with the peasants. If all the other elements on the periodic table are the peasants, then the noble gases are the kings and the queens of the society. And lastly, we're going to take a look at hydrogen. Okay, so remember, hydrogen is over on the far left-hand side of the periodic table at the very top of the chart. However, it does not belong to the alkali metals. Please understand that hydrogen is a nonmetal, and it is a gas, and it obviously does not belong to that group. However, the electron configuration is one and such that it gets put over there. Now, in nature, it occurs as a diatomic molecule, so we're going to have H2, so it's one of those 7 diatomics, along with the few that we see on the right-hand side of the table. The 1s1 orbital configuration basically means that there is no shielding of the nucleus. So the interaction between our proton in our nucleus and our electron along the outside is very strong. So that being said, unlike the alkali metals, it really doesn't want to give up its electrons very easily. It's actually 2 times harder to remove an electron from hydrogen than from any of the alkali metals in that group. So obviously they're not of the same family. Usually when hydrogen forms bonds, it'll do so in a covalent way. It'll share electrons in order to form compounds. And we see hydrogen in tons of stuff, especially carbon-containing compounds. Now, hydrogen can gain or lose electrons. It is possible for this to happen, and depending on what the hydrogen is interacting with will dictate whether it loses or gains electrons. So in aqueous chemistry, a lot of times we'll see something, we'll see the process where hydrogen is going to lose an electron and form an H+ ion. Okay, so a proton is what we'll call it sometimes in acid-base chemistry. So that H+ ion is caused by the removal of that exterior electron from that 1s1 orbital. Hydrogen can also gain electrons. That is possible. It has an open space for another electron. And this is found when we interact hydrogen with metals. And this H minus ion forms because instead of just being 1s1, you now have 1s2. You only have one proton, so you have an extra electron. And basically you end up with a negatively charged anion, and this is known as a hydride ion. And so please understand the difference between these two. Hydrogen ions can form that are positively charged, so we call them protons sometimes. Okay. The hydride ion corresponds to the negative version of the hydrogen ion. So in this case, it's an anion. We get that when we interact with the hydrogen gas with a reactive metal. Okay, and then obviously our elemental state is H2. This is just hydrogen by itself. Make sure you're familiar with all of the nomenclature and comfortable differentiating between the various states.